All right. We have covered some fundamentals, mechanism, or expansion about the mechanism of galvanic cell just now, about nobility. Now we go into galvanic corrosion information. So galvanic corrosion, sometimes in other textbook, or you go to conferences, you go to technical seminar, sometimes they use bimetallic corrosion. Bi means two metals, minimum two metals. Bi means two metals reaction that create the corrosion, metallic corrosion. And this one really seen that when we have two metals that electrically connected, in this case we use electrolyte, right, in the same environment, and they are characterized by nobility again. So the flow of electron or E negative charge is decided by the nobility of two metals. Okay, nobility of two metals. So we start with a simple diagram. We have two metals. One is M, one is N. So you have two metals there. So later you will see something flowing between these two metals, and we will recall some of the electricity or electrical terms, define the potential and the current that happen between them. First, M represent the less noble metals. Again, nobility, you have high level, low level. M, let me see. Okay, M represent lower level, and we call lower level as anode. Okay, so two metals, high level, low level. So low level metals, we call it anode. So later we will, if we have time, in either in this session or next session, we will look at anodic reaction, right? Those have lower level, and cathodic reaction, those at higher level. So now we look at anode definition. Those at low level in the nobility, they become anode, or label M. Or in the equation later, you see sub M. Sub M means lower level metals that represent as anode. Okay, and you know that those lower level, they are the one who sacrifice, the one who give electron to the high level. So this one will destroy themselves. They are the one who control the corrosion rate. They are the one who control the giving of electrons. So they are the one who control the corrosion process or corrosion rate. And if you have coupling, coupling means there's a connection, there's a wire connection, or there's a electrically connected between lower level and higher level. All right. Through if there's a connected through a connector, then you know electron, when you have a connector is like a highway. It's like highway. So electron will use the shortest distance to reach its destination. That is the characteristic of electron, right? So if you have a highway, a connector, or we call it coupling or bridge, so the electron will use the highway to reach the higher level, higher nobility. Okay, so if you build a highway for the electron, then acceleration rate will increase. Okay, you will just increase the exchange of electron. Next, about another metals at a high level, we label as N. You just memorize it as N stand for noble. Noble, less noble. N stand for normal. And the one at the top, they are the one who receive electron, right? So the one that receive electron, we call them cathode. Okay. So cathode, anode. All right. Nobility. Just look at nobility. Those at high level, cathode. Low level, anode. So later, when you derive equation or when you do calculation, you need to identify which one is anode, which one is cathode. Then there's one set of equation for anodic reaction, one set of equation for cathodic equation. So before we go into detail of equation, you know that anode is the one at lower level who give electron. So in your equation, in the anodic equation later, you will calculate the exchange of electron, right? Then this one, in your cathodic reaction, you will receive electron. So there's a receiving electron in the equation. This is the release equation or the loss of electron in the anodic level. Okay, so we will use this diagram to continue to derive a relevant equation in galvanic corrosion. So this slide's just to tell you, when you're given different nobility, you can identify them as anode, cathode, right? Anode, cathode. Anode is the one who give electron because they are at lower level. They are the one who corrode. They are the one who destroy themselves. They are the one who contribute to corrosion rate. Okay? The one at a higher level, we name them as cathode, or cathodic reaction will happen at the higher level. Okay? M and N. So this is also one of the schematic diagram that we expect in your answer when it comes to test or final exam. So when we give you two metals, you draw the diagram, label the diagram, and you show the direction of the electron exchange. Okay? You already know the understanding before the break just now. So you have lower level, you have high level, and you know the direction of exchange of electron, right? Okay. So here at normal metals is the one who collect the electron. So the corrosion rate will decrease until there's no more exchange of electron, right? So the corrosion rate will stop until there's no more exchange of electron in the cell, or we call it the reach equilibrium states. Okay, there's no more electron. The lower nobility metals or the anode can no longer give, or no more electron to give. Okay, no more electron to give, then the corrosion will stop. Okay. We still use the same schematic diagram. We start to derive equation now. So we look at cathode. All right. So what are the material outside there that in the industry that can work as cathode? Cathode is the one who receive electron. Yeah? So, or where does this galvanic corrosion it take place, and then the material become cathode? These are the technical names that maybe some of us we are not exposed to. Magnetite and calamite. So what is magnetite? It's like a stone or crystal structure. So inside this magnetite, inside there, you have a high percentage of oxide and ion. So this is actually an oxide, right? It's an oxide, iron oxide. But inside this iron oxide, if you do characterization using machine, you will observe there's a high percentage of ion inside magnetite. Okay, magnetite itself, the word here also tell you that is near to the wording of magnet. Okay, near to the word of magnet. You know that magnet have electromagnetic flux and all this. Where does this electromagnetic flux come from? Ion. You know the ion is when you have a different potential, then ion can become magnet, right? Sometimes you change the nature of the ion. But anyway, you understand what is magnetite here. Magnetite is oxide, iron oxide, with a high percentage of ion inside there. Another one is calamite. What is calamite? Calamite is something look like white stone here. That chemical formula is Fe2O4Zn. So if you look at calamite chemical formula here, what do you have? You have ferrum or ion, you have oxygen, you have zinc. So you have ferrum, you have zinc, you have two types of metal here, you have oxygen. Go back to corrosion. What are the agent of corrosion? Oxygen, water, hydrogen, temperature, right? So, and metals also, right? So calamite itself, it can contribute to the galvanic corrosion, yeah? And this one, these two, magnetite and calamite, they can work as cathode. Yeah? They can work as cathode when they come to galvanic corrosion, right? So these are other examples, like graphite, sulfide, and so on. Yeah. Okay. Next, we talk about current. Okay, we talk about current. Now, in your introduction to electronics, you learn about voltage, you learn about current, you learn about resistance. In metals corrosion or in galvanic corrosion, the current between the flow between the two metals is called galvanic current. We use capital I. All right. And it circulates inside the electrolyte, meaning these two metals inside the solution. There is an exchange of electron from lower to higher nobility metals. So it happened inside the electrode from less noble to high noble, so on. This current, it follow electron direction. Okay. So this slide is just to show you how to sketch schematic diagram for galvanic cell. Right. So in exam, you will be instructed or you will be lead or guide. For example, the section construct a schematic diagram for the galvanic cells in the corrosion process. So the instruction, they give you some hints. You already mentioned the galvanic word. So you expect you to draw something like this. All right. So two metals connect together, and then the electric direction, right? Next, we look at one more diagram that is available in your handouts, in your tutorial handouts. So just now in one table that we talk about eight factor that affect galvanic corrosion. One of it is under geometric that I point to in the first session, right? Is the geometric dimension. We talk about surface area of anodic and cathodic metals. Okay. Now, you know that the surface of exposed will influence the corrosion rate in all types of corrosion, I can say. Right? As long as there's exposed area to the corrosion, it will control the corrosion rate. So same with galvanic corrosion. All right. So we have two types of surface area when we talk about corrosion. And just now we have two station, anode, cathode, right? We have anode, cathode, and just now in the schematic diagram we have M and N. M, N, N is the noble, means higher level of metals. All right. So in this schematic diagram, you have two types of surface area. One is M or N. So we, in the mathematics model, we use S to represent surface area. Sub M, capital M, means less noble metals. Less noble metals, or another word we call them anode. Right, surface of the anode. S sub N is a surface of the noble element or surface of the cathode. Anode, cathode. Okay, anode, cathode. Now we talk about surface. Surface of the anode, surface of the cathode. SM, SN. Then you look at this diagram here. All right. So you have anode A, you have cathode. All right. So the current, you look at the direction of the, we know that anode will give electron, right? Anode will give electron to the cathode. So as you can see here, you have, when you connect the two metals, microcell current I, later we look at this term, which is the total current inside the system. And you have IM. IM is the less noble metals, right? Anodic, anode. And you have a cathodic current. Later we look at one more terms here, cathodic current, IC, and anodic current, IA. So you have IM, IC, IA. So here you see that the current actually is opposite of electron transfer. Electron transfer from anode to cathode, right? Electron, we talk about electron. Electron transfer from anode to cathode. Anode to cathode. This is the dashed line, represent the exchange of electron direction. Anode, cathode, anode, cathode. However, current direction is opposite of electron. Current in electrical module is opposite of your electron transfer. If we talk about current, we talk about from cathode to anode. Yeah, just take note of that. Don't confuse with the dashed line and the solid line. Yeah, when we talk about current, we talk about from C to A. Yeah. Okay. So in the perfect case or standard case, I, the system total current or macro cell current, equal, what is macro cell? We have two body here. Just now in the video, just now we have two bodies, zinc and copper. Sorry, zinc and copper, right? Because zinc is anode, right? So you cut the system into half. You have half cell, half cell. Half cell plus half cell, you get microcell, right? So I equal to current of your anode, M, right? Anode, M. Current of your cathode equal to anodic current, IA. Okay, so meaning if you have the current is equal, then the corrosion, you can analyze the corrosion environment. Yeah. So this is the first equation for galvanic corrosion. Later we will expand this one, and this one. Now we get the concept correct first. So we look at current. Current, you have a few types of current. The one that inside the anode, the one that inside cathode, and the current that transfer the current that transfer exiting the less normal metals, right? And the system of microcell current. So this is the first equation we derive. And the surface also, we have two types of surface, anode surface and cathode surface, okay, or M, N, M less noble, N noble, or high nobility. Okay, I pull the diagram to my right hand side and I continue to work on my equation here. So anodic current exiting metal M given by this equation. So anodic, we are talking about anodic current that go outside from the metals M, which is low level nobility metals. Current that go outside from these low level metals, you have two, low level metals, current go outside from this one, equal I corrosion multiplied by surface of the M, the less noble metals here. S means surface area. Okay, so I corrode, let's see, yeah, here. Okay, I corrode is what I mean by I corrode is a corrosion rate. Corrosion rate on the less noble metal M that exposed to surface, the surface of less noble. So I here is not current, but I corrode, sorry, I sub CORR, this is not current, don't confuse with the capital I and small I, don't confuse with capital I and small I. Capital I is current, however, in the equation, when you see small I is corrosion rate. I corrode means you have two nobles material here. The one that corrode is which one? The one that corrode is less noble one. Is the one who give electron to higher noble metals. This is the one who experience corrosion. And this is the one who control the corrosion rate. So when you do calculation for metal M, which is a less noble metals, you calculate the corrosion rate multiplied by the surface that exposed on the less metals, less noble metals. So you hear small I corrosion means the corrosion rate of that metals, of the less noble metals, multiplied by the surface. Then you get the current. Okay. First equation, second equation. Next, we look at cathode current. You have two metals again. We go back to the concept. You have less noble, which is anode. You have high nobility, which is cathode. We have done equation for less noble or M metals. All right, less noble or anode. Now we look at high level. What happened to the high level members here? High levels or cathode. So capital I represent current. I current equal to IC, small I. Small I, C, it means corrosion rate for, IC here is another things. IC here is cathodic current density. So there's a difference meaning. On the top here, ICORR is a corrosion rate. I sub COR corrosion rate. Another one, small ic. Small ic here is cathodic current density. So one is corrosion rate, one is current density. This is IC multiply by total surface you have. Total surface SM, lower noble metal surface plus higher level surface is combined two, multiply by current density. You get current at the cathode that flow at the cathode high level metals here. Okay, high level is a combination between two surface here. Okay, look at the equation, see if anything you are not clear. We derive the first equation just now. We define the capital I, which is the current inside galvanic cell. We look at what happened at low level, low nobility metals, which is your anode. We look at what happened at the high level nobility metal, which is your cathode. M, N, M, N. So we look at these two equations. So we have three equations so far. You have three equations. Basically, you can link these three equations. From the first equation, current at anode equal to current to cathode. Basically, this equation equal to this equation. You rewrite them. You take this one, put to the left hand side because these two are same. So I corrode, this is the corrosion rate multiplied by the surface of the less noble metals equal to the density current of your cathode. This is then density current, not corrosion rate. Density current multiplied by, you can say, as a total area of the exposed metals, both metals, right? So surface of metals M, low level, plus surface of noble, higher noble metals. You get this equation. This equation, you rearrange again. The purpose is to get what? Is to get this one. The purpose of rearranging or using these three equations is to find the corrosion rate, which is I sub CORR. How you find the I CORR? You move your SM to the right side. How you move? Divide, right? You divide both side equation with surface of M or anodic metals or less noble metals. This one move to the left hand side, divide. You will get IC multiply this one divide by SM. So get 1. So this one become ratio SN stroke SM. It become a ratio between the normal, between the noble metals and less noble metals. It become a ratio. This one is to calculate corrosion rate of the less noble metals in the galvanic coupling or in the galvanic cell. Okay, this is how you do calculation later. Okay, so once you understand this equation, if you are given some constant, you should able to calculate corrosion rate of that galvanic process. Okay, so what is important on these slides? Corrosion rate can be calculated if you have current density, if you have the surface area that exposed to the environment of the less noble metals, or we call it SM or anode surface, and the higher level metals N noble, or we call it cathodic surface. Okay, important this equation here. right? Important, yeah? So next one, show you some example of galvanic attack in the industry. So this one is on standard steels. Okay, so standard steels, when it come to galvanic corrosion, it cannot escape. Standard steels, when there's an environment, when there's a potential difference between two metals, they're exposed to the same environment, especially in the seawater, stainless steel also cannot run away from corrosion. So this is an example of stainless steel 304 grade when it coupled with graphite. Okay, stainless steels coupled with graphite in aerated acid solution. This one you dip and then you pump oxygen inside the acid solution. You dip two metals and put them together. You dip stainless steels and graphite, you put them together. Then graphite means sometimes because of the sealing, because of the devices that put together for the operation, then you will see corrosion happen. Yeah? Another one is this one is at the well spot. When you have a magnetite layer. Just now, before the break, we introduced you what is magnetite, right? Like the crystal black color that appeared here in the previous slides, if you still remember. So that one is the ferric oxide or iron oxide that have high concentration of ion. All right. So this is the galvanic corrosion that happened on the surface of welding, right? Because of the galvanic corrosion. Right? Okay, we start to look at a few graphs. We start look at galvanic effect on less noble metals. Okay, let me check. Okay, so we already seen the effect of corrosion just now. And under the session effect of metal corrosion just now, we can calculate current. We can calculate the corrosion rate. If your other parameters you also can calculate. You can calculate the current in the less noble metals or high noble metals. The surface area exposed also you can calculate if other parameter you know. Right. Now we look at less noble. What happened to less noble metal M here or anode layer? We will look at a few examples. First example, we look at platinum and zinc. Okay, platinum and zinc. Both these two metals you dip inside acidic solution. Why acidic solution? Because inside acidic solution, you know that inside acid, there are lots of electrical charges inside there, right? So you learn about pH. Again, recall what is pH. pH value is actually H positive concentration. The more H positive, the lower your pH value. And OH negative represent alkaline level, right? So you play around H positive and OH positive in pH. We already covered that one in the previous chapter, right? This is just to recall what is acidic solution. All right, so now we talk about two metals, zinc and platinum. If you have the handouts, if you have the tutorial handouts, go to the table of the potential E just now, the voltage just now. There's a table, I forget table what already, but there's a table that give you element and the voltage. Can you go and find platinum and zinc? Platinum PT and the zinc inside the table. You will see the voltage beside the table, in the table. Again, in the table, we just mentioned already, the more positive value it is, the more noble it is. The less value it is, become less noble metals. So if you refer to the table, if you have these two metals, platinum and zinc, you know that platinum sits above zinc. And zinc is, can say, below the table, right? Anything that link, you can say like almost 70% in the case out there. As long as there's a zinc happen in the system, zinc will always become the low level metals or low nobility metals that it will experience corrosion there. Okay, and in fact, in most of the case, we purposely put in the zinc into the system just to sacrifice the zinc, just to protect the other material. We put in zinc inside there just to disturb the system, and zinc will give electron and sacrifice itself. All right, and we keep on, and zinc, actually zinc is not expensive also, so you can always replace zinc in the system. Okay, so we look at platinum and zinc. So by looking at this statement, they are coupling together, they are put inside acid solution. That one fall under chapter 5 content, where you have two metal put together in the solution in the same environment, and they are electrically connected. In acid solution, they are electrically connected. So it fall under chapter 5 chapter, right? So from here, you know which one is higher, which one is lower, right? I already give you the table already. So you know from the voltage potential, you know which one is higher, which one is lower, right? But again, I have to stress this way. In the table of the voltage just now is perfect case. So it's just a reference value for that, right? Because you have different environment, it will behave differently. Okay. Yeah. But anyway, the value cannot, it gives you some idea which one will be higher, which one lower, right? Right. We are not in the chemistry, so the differences between decimal place will not be any problem for us, unless you go into the chemistry that you are in the corrosion treatment, then you need to look at another table. Okay. All right. So zinc, when you couple zinc and platinum, you know that platinum at high level, zinc lower level. So zinc will sacrifice itself. So in this case, we look at first example. In this case, zinc will become anode and cathode simultaneously. In this case, zinc at low level, zinc will become anodic and cathodic process will happen simultaneous at this level, at zinc level or at low nobility level. Take note on that. This is the, you can say as an assumption before we derive the equation later. This is the perfect case that we assume when you combine platinum and zinc, platinum high level, zinc lower level. In this case, we assume at zinc, both anodic and cathodic process happen simultaneously at the same time. While for the higher nobility metals, platinums, only platinum enjoy himself. He just take part in the cathodic process. Okay, so first example, we look at less noble metals. In this case, galvanic effect, we assume low level metals, he will do two process simultaneously, anodic and cathodic. Yes, itself is an anodic process will happen, but in this example, in this case, we assume, because later we look at real data, we look at hypothetical, theoretical dimension first. So in a theoretical dimension, we assume zinc happen anodic and cathodic process simultaneously. So this is a setup of our discussion. Anode, cathode, zinc, platinum. You know that exchange of electron happen, right? Lower give higher. So this one will give electron to this guy. But it will happen simultaneously with the cathodic process. But at a higher level, cathodic process will happen in this case. So I pull the element to one side, and let's continue to look at one simplified potential versus current plot in the log form. E versus log plot. Excuse me. In this case, these slides, I have to stress this one. This is a simplified case, and we ignore current correct with coincide with current density, and ohmic drop do not happen in this case. We are looking at theoretical scenario, not the real scenario. Theoretical dimension first. In theory, we can take out some environment consideration. In this case, we ignore ohmic drop, we ignore currency density, we ignore current, other current that crash with the density. So we ignore these two things. Okay. Now, what is ohmic drop? Go to appendix D or B just now. Go and find, or you can just Google what is ohmic drop. This is the first diagram in your handout. In your handout, maybe the diagram is very small because I try to squeeze all the graph together, but this one will be at the left-hand corner top diagram in your handout, in your tutorial. But this one I make it very big so that you can see clearly. So we are looking at two types of metal here, platinum and zinc. So if you study the axis here, you have potential E and current. It's not current, sorry. Log I, just now in the equation just now, small I represent what? You need to be careful. You have two small I, You have two small I there in the equation. Flip back to the slides. Okay, you have two small I in the equation. Small I corrosion, it is a corrosion rate. This one. Small I corrosion is the corrosion rate. Small I C is current density. So don't confuse with the I, small I. You have two meaning here. I corrode and I C. Go back to the slides. I try to explain the process of theoretical process between platinum and zinc. So on this graph, there are two lines that represent the material. Zinc line, platinum. Okay. Now, you know that when we talk about high level nobility and low level nobility, what happened to low level metals? They contribute electron, right? The one that destroy itself by giving electron. What happened to the high level metals? High level metal actually do not do anything. He just receive electron, and even you change the cathode station here, you replace with another one, the exchange will still happen and you still measure the same voltages. So the cathode station here basically do not do anything. It just receive and deposit the positive charge become solid or powder, right, by receiving electron. So you see here basically is receiving electron, right? Something receiving electron. So this line receive electron, this one actually release electron. Make sense to you? Introduce you two line here. Zinc, one is release. This line represent anode that destroy himself, release electron. So you see release himself, two electron become charges. And cathode basically do not destroy himself, he just sit there and receive, come on, give me electron, right? So here you see something will happen to the system, right? Plus electron here, right? On PTN, This we call it what? The scenario experiments up. These two elements, platinum and zinc, they are in what solution? Acidic solution. What is famous for acid? H positive. How you know it is pH in an acidic level or less than 7? It meaning you have more H positive concentration. The lower pH value meaning high H positive concentration. If you go to alkaline region means pH level more than 7 means that you have OH negative charges in the solution. Then that one go to the alkalic. But now we are at the acidic solution. Acidic solution means we focus on H positive. And just now we mentioned the Catholic station. Catholic station is just lie there, come on, give me electron, right? So in here, what happened to the electron that donate by less noble? It will go to the surface of this member here, this platinum here, this noble metal. It's a lie there, and you just receive. And what happened to the electron? Electron will contact with the positive charge around the cathode. The positive charge around the cathode here. So what is the positive charge around the cathode? Acid, right? Acid have what positive? H positive. So H positive will combine with the electron donate by lower level of member. Electron go up, transfer, but cathode do not do anything. It just, okay, come receive. But the electron cannot jump over into the solution. It can only go to the surface of the platinum and meet up with his friend, positive friend, which is in this case in the acidic solution, which is the H positive. So that's why in this line you see there's nothing happened to platinum, but something happened at the surface of platinum where the electron meet up with his good friend, positive friend. H positive plus electron, you get hydrogen. Make sense to you? I try to understand the process by using graph. This graph, two important line with this line. What happened to zinc? What happened to hydrogen? Sorry, what happened to cathode station? Okay, so in exam or test, I will give you a blank axis, a blank graph, or I just mentioned plot voltages, potential versus log I graph, or construct a potential versus log I graph by looking at the two elements I give you. How to write the equation, how you know how many charges to give. There's a table I give you just now, right? There's a table I give you just now, right? So inside the table, you have potential value and you have the chemical reaction, like how many charges let go in the table. So you just go and shop in the table there. Decide which one is higher level, lower level, all right? Which one is M metal, which one is N metal, right? Which one lower, which one level, by looking at the voltage value. Then you draw the line, sketch the lines on the graph itself. Two lines you draw first. One, lower level going up. Okay, lower level, anodic station. Lower level, in this case zinc. You draw a line. And from the table, again, you draw one line crossing negative gradient. And again, Catholic station, you just lie there and receive electron. So only things that you happen is at the surface of the cathode. All right, electron go through the bridge. Electron go, where does electron meet his good friend positive charge? At cathode station, at the surface of cathode, just lie there, and yeah, come and meet at my station. So he just meet the positive charges around the cathode. So you ask yourself, what is the solution given? If the solution given is acid, you think what do you have in acid? H positive charge. So you write H positive charge combined with electron, you get hydrogen charge. Hydrogen gas, H2. On what? On the cathode station. Make sense? Okay. Everyone good? Okay. Ngan, you okay?
Yeah, okay, sir.
All right. So there are two lines important that when they ask you to construct, start with these two lines first. Lower noble with positive gradient, positive going up line, and cathode with negative gradient, crossing at one point, right? It doesn't matter where is it, doesn't matter, as long as you sketch this line and this line, and then write the equation. The equation is inside the table already. You just copy, go in shop and copy, put on the line there. Okay, one challenges is this one, okay, but I just give you a hint. It will be acidic solution in the test or exam. So same hydrogen positive charge plus electron, you get this one. Only you need to change the name of the element here. Okay, so I give you hints already. Okay, next we slowly look at this graph. Again, this graph is hypothetically or theoretical dimension. Later or in our next class, I will show you the real scenario compared to what we discussed today. Yeah, but here we start to study about the theoretical dimension first. Right, at least everything makes sense to you first. Right? Okay, let's look at point 1. What is point 1? Yeah? So point 1, okay, point 1 represent free corrosion condition of zinc before coupling, means before the corrosion start. Before coupling means before the transfer of electron start. So position 1. Position 1. What does position 1 give you? Is a coordinate. It's like reading a coordinate chart, a Cartesian chart. You have x and y coordinate. So this point, before it start, you have I prime corrosion. Again, what is a small I? So this is a small I. Small I prime or comma corrosion. What does it mean? It means it's a corrosion rate. Corrosion rate before start, before give energy, before give electron. And then what is the potential on the left hand side? We use E prime, means before start, before anything happen, right? E prime corrosion means potential before start. This is point 1. Okay. Then what happen if you start coupling already? What happen if the zinc meet with platinum? There's an exchange of electron happen. So point 2 here. Point 2 also give you one coordinate, which is x and y coordinate. What is your x here? If you give you I small I corrosion, which is your corrosion rate when the coupling start. After you do coupling, corrosion start, you can calculate your corrosion rate here. This is before. Point 1, this value is before with a prime, with a comma beside the small I, means before corrosion rate, before they start combine together or join together, or before the corrosion happen. So this one move down is the corrosion already happened. So there is a corrosion rate that you can calculate. Right? We already have the equation just now. Right? So, and then what is the potential of point number 2 after you join zinc and platinum together? Read to the left hand side, become E corrosion, which is the potential of your corrosion process. So what does the changes of these 2 points? What you can read from this graph? The corrosion rate before and after. And you see there's a differences of potential happen here before corrosion happen or before coupling. E prime corrosion means prime, you see the comma means before anything happen. And at point 2, after you join the two metal together, means coupling corrosions already started. Then you get E corrosion, which is potential for your corrosion. Okay. So this value you measure from using instrument. This value you measure with the instrument, and don't confuse with table of the element just now. Don't confuse with that. Don't confuse with that with this potential E here. E corrosion means it difference. It will change the value when you meet up with different member. Okay, don't use the table value V there for this value. This is only when they meet together, then there is a value that you measure from experiment. The table that I give you just now about nobility one, that one is perfect case, only that particular element compared to a standard element. So in the table, you'll see one voltage 0, 1. So you will compare to that particular value, compare that reference material. Okay, or we call it datum material. Okay, all right. We have 2 points. Okay, we have 2 points that give you corrosion rate and also potential after, before coupling. We have 2 points. Next, look at another point. So when you before and after you do coupling, then the corrosion happen, right? So before you mix them together, before they are electrically connected, nothing happened yet. But when you join together, when you connect them together, you reach point number 2. Okay, then corrosion happen. After corrosion happen, you will go to point number 3. Okay, final condition you can obtain by summing cathode current density at point number 3 on platinum. So after you join and you let the corrosion happen, so on cathodic station here, you can measure your density current. Okay, density, current density at cathodic system. Where does your, on the graph, right? On the graph, where is your cathodic station? This line, right? You have anode station, cathode station. So go to cathode station, and then you go to point number 2. You use your ruler to draw a straight line connected to your E corrosion just now. I repeat, how to find the location of cathodic current density which is projected down, this value. How you get this point? You trace from the graph. So for the graph, you have two stations: anode, cathode, low nobility, high nobility. You have anode, you have cathode. So you trace from your anode station, draw a straight line to the corrosion potential. You will bypass a few points. You will bypass the anode station at point number 3. Mark that point at point number 3. That point will give you current density for cathode station. Okay, cathodic density current at point 3. Point 3 is a Cartesian plane. They have X and Y value. So at point 3, you are sharing the corrosion potential because you already started the galvanic process, right? So the potential maintain until the corrosion finish, until your lower level, he say, I have no more electron to give you. Then if no more electron to give, then you stop the corrosion. So when you join two metals together, you join these two metals together, low and high, they share the same potential. You measure the same potential, where that's why you draw a line with your ruler just now. And it bypass the cathode station at point 3, project down from this point, project down, you get the current density at cathode station, or we call it cathodic current density. Okay, what is a symbol of current density? IC. You still remember just now? IC. So, but however, this one, we just on the graph, just to differentiate, this is IC, I sub C, but this is just to differentiate, further explain or further label what is this point you project from. You project from hydrogen and platinum surfaces, or hydrogen process on the platinum or cathode station. That's why on this graph you see IH2, platinum. It means it happened at the platinum surface where the electron meet up with the positive charge or positive friend. In this case, where do you find the positive charge? Go and find around what happened in the cathode. In this case, cathode is platinum. So around the platinum, what do you have? You have acidic solution. What does acidic solution you have? What mean by acid? Acid means you have a loss of H positive. So loss of H positive around there, you will meet at the surface of the platinum. So you get your current density. This value is current density. So in the exam, I will give you some I will give you some value or two metals in the acidic solution. I ask you to construct E versus log I graph and label the following point, or label the following point accordingly: A, B, C, D, E, and so on the graph. So these are the points that you should label inside your graph. Okay, so we have stopped at point number 3 here. Okay, what happened at cathode and what happened to anode, same idea. So if you join two metals together, corrosion happen at both stations. So this point will give you what happened at the cathode station. This point, because this line here, it will give you what happened to at the zinc cathode there. Okay, why suddenly there's a one line over here? Why suddenly there's a one line over here? You still remember just now we assume at the anode, how many processes happen at anode just now? We assumed earlier before we start discussion. We have two processes simultaneously happen at anode, which is cathodic and anodic process happen. This line is your anodic. This is cathodic process. So again, what mean by cathodic? Cathodic means receive electron. So what is around? What is around the zinc body? Acid. Both you submerge in the acid. So around the zinc, what you have? You want to receive. What you call? Receive electron, or electron will go to the surface of the zinc, and the electron will go and pull the positive friend around the zinc. Okay, so again, what is acidic solution? Acidic solution, you have H positive. So when the zinc gives electron, the electron will go to the surface of the zinc, and the zinc, the electron from the zinc, from the lower noble, it will combine with the H positive around the zinc. That's why you have this line over here. This line negative gradient here is the cathodic reaction where it happened around the zinc. This line was drawn on the graph because we assume there are two processes happen at anode station. And only one cathodic process happened at cathode station. Just now, before we do discussion about this graph, we have that assumption. That's why this line happened on the graph. So you join the same corrosion potential, you omit point number 4. Point number 4, you project down. This is the potential. This is the current density that happened at the anode station, or your I sub C. In this case, hydrogen, zinc. It means it happened at zinc. Okay, so maybe I'll give you a few seconds just to digest the point that you see and this statement here. So at point 4 on zinc, equal anodic current density on zinc, so condition of electron neutrality. So it means that they share the same value of potential to the y-axis. Okay, so 2, 3, 4, they share the same potential line of your y-axis value. Okay, any question on constructing the graph so far? Good, eh? Okay, so I want you try to look at, try to understand, like in the exam or test, I'll give you a scenario. Then are you able to draw the line on E versus log I graph or not? First, check nobility. Where do you check nobility? Table with the potential value. More positive voltage, more nobility. Then those at the lower level one, it become anodic, it become metal M. Those high level become metal N. So what happened to the low level? Give electron, destroy themselves, donate electron to high level. High level do nothing, just lie there, and hey, come on, give me electron. And where does this electron meet with the positive charge around them? At the surface of the cathode, right? Surface of the high level metals. You lie there, okay, you go and meet your friend at my gate there, at my boundaries there. Okay, go and say hello to your positive friend. So it combined with that. And then the solution. Solution normally in tests, just give you a hint, in test or exam, it will be acidic solution. There's a more simplest scenario that I can give you. So what do you have in acidic solution? H positive. All right. So that is also definition of pH value. So you have H positive, and you look at the question. The question say at anode you have two process. So you draw two lines. One is anodic process, one is cathodic process at anode. So, and then the question say there's only one process, cathodic process happen at cathode. So you draw another line for your cathode. So on your graph, you have 3 lines, and then identify the point. Okay, identify the point before coupling. What is the value? Right, before coupling, which is 0.1. Label 0.1 on your anodic process, any point, any location, doesn't matter, right? So you just pick one point along this line and then project down, label as corrosion rate before coupling. Maybe this one in the test, I will just label as A. So put your A over here, and then label point B, where to point B or label point number 2, and then label the point of corrosion rate after coupling on your graph. So you project down, you label this one as point B. Point B is corrosion rate after coupling. So you label A here, B here. Next, on your graph, yeah, go ahead. Any question? Oh,
We
yeah.
have other class now.
Oh, sorry. I go over the time. Okay, we stop here and see you guys later. And apologize for other lecturers. Okay, let me
It's
end the
okay.
recording. Yeah, okay, thanks for the